Welcome to the Distinguished Lecture Series. I'm Karen Matthews of University Video Communications. Our program is designed to enrich graduate and upper division curricula with academic presentations by top computer scientists from industry. Its speakers and topics were nominated by computer science faculty of more than 50 universities. This presentation is sponsored by the Intelligence Systems Laboratory of the Xerox Palo Alto Research Center. Dr. Daniel Bobrow, a major contributor to the development of artificial intelligence programming, received his PhD in mathematics from the Massachusetts Institute of Technology in 1964. He founded the Artificial Intelligence Department at Bolt, Beranek, and Newman and became vice president of their computer science division. He's been with Xerox PARC now since 1972 and is a research fellow in the Intelligence Systems Laboratory. Dr. Bobrow is president-elect of the American Association of Artificial Intelligence and chairman of the Common Lisp Object Specification Committee. His talk today, The Common Lisp Object Standard, is based on the work of this committee. It's our pleasure to introduce Dr. Daniel Bobrow. Danny?
Thank you, Karen. It's good to be with you today. The talk I'm giving today is actually a snapshot of history in action. The title, The Common Lisp Object Standard, is not yet true, but we hope that it will be true during the lifetime of this tape. Of course, as Casey Stengel said, one should be very careful never to predict anything, especially about the future. So, to go into the talk here, you'll see that what I'm going to do is first talk about the history of object systems and how we got to where we are right now. Then I'll talk about the design criteria for this object system that is going to be put into the Common Lisp system. Then I will go into the principal language features of this object system. And from there, I will go into talking about what we call meta-objects, a way of making the object system be flexible and being extensible. And part of the reason for that, for having that level, is to allow a new notion of what it means to be a standard, namely something which captures what we currently want to do and also allows some flexibility in what we would like to see happen in the future. And finally, I'll talk about the status of the standard as of now, how the process is going, so you'll see something about how a standards process can work. And finally, we'll end with a summary of where we really are. So let me start with the Smalltalk object-oriented programming system. It's the classic object programming system. It's what people think about when they think about object-oriented programming. And so I'm going to give you a brief overview of what it means to be an object-oriented programming system. An object-oriented programming system is based on the idea that objects have state and behavior. For example, a square can have an origin and a size. And so that's a kind of object that's in the system. And each of these objects not only have this state, which they keep for themselves, but they have a behavior. And that behavior is invoked by sending each of these objects a message. So a particular square could be, say, square 1, could be sent the message, move to point 2. So you'll have that square at that point do an operation which is appropriate for the move to operation for itself. Now, objects don't exist all by themselves. Objects are instances of classes. And these classes describe these instances and how they are built and how they behave. So, for example, the definition of the class square would state that it has two pieces of state. And those pieces of state are labeled origin and size. And it would state that there are two methods which all objects of this class know how to follow. Namely, they both know how to move, and they both know how to grow. They, of course, in any real system, they'd know how to do much more. So what you see here is that it says that the key to the message is move. And then there's some code that's associated with that key that's special for the class square. Now, classes don't live by themselves. Classes can live in a space of other classes. This is a key idea of object-oriented systems, in that classes can inherit from other classes. So you can have a colored square, and a colored square is a kind of square. So it says that its supers of colored square is square itself. And it has some special state by virtue of it being colored, namely a state called color. So a particular colored square, say colored square 17, would have an origin, say 0, 0, and a size, say 100, and it might have a color called red. And you see that this square shares with, this colored square shares with square much of the same properties. And in fact, it can respond to the same messages for move and grow. And unless there's a specialization that says, here's a special way to move, it will move in the same way that squares move. How is this implemented? This is to give you a model of how this kind of thing is done. When a message is sent to a square, say square 1, and here is the square, it says, what class am I? How do I find out what class I am? Well, there's a way of going to the class. And in the class, there's a set of methods, and the class looks up the method associated, say, with the move operation. So here in a special table associated with the class is a table of methods which associates the key, this move or move to, and the code that's supposed to be used for doing the move operation that's special to square. Okay. Now that's a very fast overview of what we mean by object-oriented programming. Now let's contrast that with LISP, which is a procedure-oriented language. Now LISP, as a procedure-oriented language, has primitive data types like symbols and lists and numbers and strings. And each of these are sort of implemented separately from any notion of what behavior is. You can also add new data types, such as squares and points. But each of these just captures some state. In addition, there's behavior, as there is in any programming language. And that behavior is captured in procedures or functions. And the way you cause that behavior to be invoked is by saying, move square point. So we have this kind of notation, move square 1 to point 2, where this move is a name for a function which captures the behavior that all move operations are supposed to take on. Now, it became clear in the last, say, 6 or 7 years that object-oriented programming is a good way of organizing programs. It allows you to factor out the kinds of operations you want to do in terms of these classes that describe objects. And so what we'd like to be able to do, what we have liked to be able to do, is to bring object-oriented programming into LISP. And so there have been several attempts to do that. One is called flavors, and another one is called loops. And there have been a number of others, but these have been some of the most popular. And what they have done is they've introduced the notion of a special class data structure, which acts very much like the classes that we talked about just a minute ago. And they introduced a special syntax that looked very much like the syntax we saw a little while ago for Smalltalk. Namely, it says send, this is a special symbol, and it says send square 1 the message move to point 2. So it looks like the same syntax that was in Smalltalk. But there was a problem. Messages only could go to instances of classes. The rest of the data types in the system were completely separate. And users themselves would have to know whether to send a message or to invoke a function. So the Common Lisp object system is based on trying to overcome some of those problems. And this new design is based on a later design for the loop system called Common Loops, which was an integration of some ideas into the Common Lisp system. This was done at Xerox Palo Alto Research Center, and the new flavors work done at the Symbolics Corporation. And it was designed especially to fit into the Common Lisp standard. Now, the critical thing about fitting into the Common Lisp standard is that Common Lisp as a standard language had to be frozen. That is, the real value for any standard is that it means that you can build portable programs, and it will run any place on any manufacturer's equipment or many manufacturers' equipment, and the same programs will run on the same software. So what did we want to do here in building this system? Well, we wanted something which was a portable object-oriented system. And what we wanted to capture was a kind of standard, well-understood style of programming. So we wanted to capture what we had done in common loops, in new flavors, and in their predecessors, loops and flavors, and in some of the other systems like Smalltalk. But we wanted some flexibility. That is, one of the things that we've learned in the way we have worked in Lisp is the power of being able to change our minds. And Lisp itself has flourished for many years without having a standard, as long as it was relatively narrowly distributed. But now that it's starting to be used for real applications, we need to have a way of having one language. But we also have this other tension, which we says we'd like to be able to add things on. So what we wanted to do is have in the object standard the ability to implement additional features like those from loops or flavors of Smalltalk, which weren't actually incorporated into the standard, but would be easily added in a compatible way. We wanted to make sure that this standard was usable. There's always a trade-off between simplicity and power. And where there was a choice between taking a minimal language and a language which had enough common features that everybody could use it, in this design, we chose common. And because there was already a fair number of programs written in both common loops and new flavors, we wanted to make the language close to those things, make it easy to move from those relatively new languages into the standard. But as I was talking about, we want to be able to have it be extensible. We want to be able to support new ideas and styles, not just new features, but new ways of doing business in an object-oriented style, and have it be compatible and integrated within a single system, not just sitting on top. Now, all this is wonderful, and one can imagine that you could build an interpretive system which would have all the properties you want, but it would take forever to run any single program. That's not appropriate for a language which is to be a standard, which is to be run with applications programs. So it has to be something that's implementable. And it couldn't just be implementable on special machines, that is, machines which have special microcode for supporting the languages they run on. It had to be implementable on standard machines, on machines that covered the gamut of what manufacturers are putting out right now. And we said it was okay if there was some room for implementation cleverness. Some of the people on the committee feel particularly clever. But we weren't going to sort of allow that cleverness to exist only within the domain of special purpose machines. Okay. Now, in order to achieve some of these results, we decided that we would do things in a strict object style. That is, we'd use objects themselves as the basis for the implementation. And that's what I'll talk about when I get back to the meta objects. And we carefully distinguish between the objects and their names. One of the lessons that has been learned in sort of the most recent versions of Lisp, for example, the scheme system, is that all objects have to be full-fledged first-class objects. They can't just be something which is named and is always the name that you use. So we've been very careful about that. At this point, I'm going to go in and talk about the principal language features of the Common Lisp Object Standard. Now, I won't be able to go into great depth, but I'll try and give you the basic principles of how it works and some notion of how some of the implementation tricks work, so that you will have at least one probe into the implementation and some view of the overall structure. Now, the first insight that we came up with was based upon the following problem. I mentioned this, that sending messages and calling functions look different to the caller. It should have said calling functions rather than messages. And the insight that we had was that we could rewrite send object draw place 1, okay, for example, as draw object 1 in place 1, but keep the interpretation that what this means is call some particular function, namely the method for draw, that's based on the class of object 1, and whatever that function is, apply it to object 1 in place 1. So what we've done is we said, let's have a common syntax which doesn't distinguish between object-oriented programming and procedure-oriented programming. However, what we'll do is we'll change the interpretation of what this function call means. So we define the generic function for draw by independently specifying each of the methods for different classes. So, for example, you might have a method for spline, another method for circle, another method for square. And then draw itself must contain the code to select and call the appropriate method, the one that's based on what kind of argument it really gets. So it actually computes internally this notion of the method for draw based on the class of the object. And so you see this little tree here. And that's to indicate that draw has in it code which selects among these three methods, and then it will actually call the code for draw spline, draw circle, and draw square. And it's in the function itself that this code is kept, not in some standard way of going to the object. This means that you can have an ordinary function, and it doesn't have to do any selection. It can be defined all in one piece. Or you can have a generic function, which is defined by a set of methods. And for that, what you have is code which discriminates based on the kind of argument that it has. Now, once you have this insight that you can have the function itself do some discrimination, you can ask the question, well, why is that first argument so special? In object-oriented programming, the first argument was the one that determined what code was being called. Well, in this case, we said, why should we have that? Why don't we actually consider this to be the method for draw and use both object 1 and place 1, potentially, as ways to decide what code is to be called? So again, we have this primitive, let's invoke some action, this fun call. We have this computation of which particular code to call, and then we're applying that result, the function to call, to object 1 and place 1. So we're selecting the method for draw using the class of both arguments. So we might have, as part of our definition for draw, we might have a way of saying how to draw a spline on a window. A spline is a kind of cubic curve. It's a standard for graphics. How to draw a rectangle on a printer. You see, drawing a rectangle on a window and drawing a rectangle on a printer may be very different. That's why you want to have both of those things as part of your description of what code to use. Drawing a square on anything, maybe the primitives for drawing a square don't depend on what they're going to, it's going to be drawn on. So what you see is that this generic function for draw, again, has three pieces, as I've talked about it here, the code for each of the three. Here we see it's draw, square, and T. T is the class which is the class of everything. That is, it's at the top of the object hierarchy. And you'll see we use that terminology a little bit more later. Well, now, once you've gone through and you said, well, you can have the class of anything, any argument, determine what's going on, you can also say, well, why should it only be the classes that make a difference? And so there's another easy extension, which is to have the identity of one or more arguments used for method selection. So, for example, if you wanted to have a special method for the quotient of anything and 0, namely a standard error function, it could just be selected out rather than having the machine have to do the division and halt, and you have to get the guy to come and fix your machine. So the point is that sometimes it's very important to have code which is special to one individual. And we've allowed that kind of things in what we call individual methods. So here we see some syntax. And this is just to give you an idea of the syntax. You certainly can't learn syntax from a single slide. But the idea is that you have something that says, I'm defining a method, and it's to go into the draw generic function. So it's supposed to be put there. And it says, well, the first argument is S is a spline. And the second one, W, is a window. And then it's going to say, let me do some things for some of the structure that comes out of the window and some of the structure that comes out of the spline. And sometimes it's useful to be able to sort of look at the internals of an object and say, and treat each of the pieces of structure as though it were a variable. And there's this special thing called with slots that allows you to sort of look inside and just use things like bitmap instead of saying, get me the piece of the structure of the window, which is the bitmap. So that's all this is indicating right here. And in fact, the syntax is slightly wrong. The parentheses to the left of the W should be to the right of it. The next piece of syntax shows what happens if you wanted to actually have some special code for drawing sketch 5. Okay, so for example, suppose every time you wanted to draw sketch 5, what you wanted to do was blink the window, because that was a very important sketch. So every time you redrew it, you might want to sort of make it apparent to the user that you were redrawing this particular sketch. So that's why you might want to have some particular way of doing this. And so what the mechanism here is to actually specify, and this piece of cursing here, this quote hash dot, ignore that syntax. That's sort of not important for the purpose. It's just something that indicates we're really talking about an individual. And this would be the special code for sketch 5. And there we see that when draw has these methods, we have, again, the selection. And what we have for the selection actually puts in the fact that there's code for sketch 5. Now notice that what I've done here is to add another case, the otherwise case. What happens if you haven't specified something? And what does the system do then? Well, then, in the usual case, it just causes an error, which says, you've just given me some arguments, and I don't know what to do. There's no applicable method. And actually what it does is calls a special generic function called no applicable method, and users can define code for no applicable method, which allows special things to happen on this kind of error condition. Now, what happens if you have an ordinary Lisp function? Can you change this ordinary Lisp function into something which is a generic function? Remember, an ordinary Lisp function is something which supposedly tells you everything you ever want to do all in one lump. That's the difference between a generic function and an ordinary function. Generic functions are defined by partial descriptions in pieces, by the methods that make them up, whereas an ordinary function has all of its definition in one body. Well, the answer is yes. We can make things which are defined as ordinary functions become generic functions. And what happens is those ordinary functions become the default method for the generic function. So here we have print, and then we've defined two special methods for printing, namely how do you print astronauts and how do you print polynomials. And when we look at the resulting generic function, we see that there is a way of choosing based on astronaut, based on polynomial, and the otherwise case, instead of being an error, as it was in the draw case, now is the original Lisp function. So that was what was there before. It was supposed to have taken care of any case. Now what we've done is we've specialized it. We've made it a generic function. So now we can incrementally extend print by adding new methods. And anything else will go through and go to this default function. Now, in the Common Lisp Object Standard, we have a set of classes which define the structure and the behavior of the instances, just as we had in Smalltalk. And these classes inherit from superclasses. Unlike Smalltalk, which had exactly one class that things could inherit, we have in the Common Lisp Object Standard something which is called multiple inheritance. And what that means is that each class can inherit from a set of other classes. Okay. And every object is an instance of a class. And a very important thing is that all of the Common Lisp objects, the symbols and the strings and all of the other data types which are built in, are also members of classes. And what this will mean, and we'll come back to this again, is that you can write methods even for objects which were formerly not even part of the system. Remember I said that in loops one of the problems that we had was that we couldn't write methods for ordinary Lisp objects. There was these two separate worlds. But what we've done now is say that every Lisp object has a class, and hence for every Lisp object you can write a set of methods. Now, for the kinds of classes that we define, we say that they can have some substructure. They have a set of things we call slots. In other languages, they may have been called instance variables, or and each slot can have exactly one value. Now, we have two kinds of slots, one of which is a kind of a local slot. This is something which you have in every instance. And so, for example, the origin of the square was a local slot. We can also have shared slots. For example, the square might have had a shared slot which was called maximum size. And what that would mean is that the maximum size that this slot square can grow to is, say, 200. So it would be something which all instances could look at and see how close they were to the maximum. The Common Lisp Object Standard defines some syntax which allows you to define some classes. When you define classes, not only can you specify that a class has some slots, but you can also specify a way of how to initialize a particular slot. This init form option says that slot 3 is to be initialized to a value of this list 1, 2, 3 here. And you can also make the defining form provide some special generic functions for you which allow you to get special access to the slots, like slot 4 here. Now, the class precedence list is a way of talking about the inheritance which comes from the problem of dealing with multiple superclasses. When you have multiple superclasses, you need to get a linearization of the set of all the possible classes. And when you have that linearization, you get the union of the slots for each class and the initial value forms, which is the most specific initial value form that's defined in any class. Okay. Now, this class precedence list, which is this linearization, is designed to to satisfy a number of constraints. Namely, that each of the subclasses must precede its superclasses. That's because subclasses are trying to specialize the superclasses. And when you have defined some superclasses, the order in which you define them defines an order in which they shall appear in this class precedence list. And you also want independent superclass trees to be kept together. So, for example, when we have this class pie, which has both apple, cinnamon, and crust in that order as superclasses, we want to have some notion of whether fruit is more specialized than spice when we're going to have a single notion of inheritance. And so what we do is we come up here, and then we say, oh, food is in both places, so we have to come over here and there, and we get a linearization which keeps all of these things and satisfies the constraints that we said. And to give you an example of what I mean by local subtrees being kept in order, what I want to do is show you this example in which fruit has now been divided into two classes, one of which deals this fruit prime is sort of generic fruit, and another thing is the red thing. So an apple is now both a fruit and a red thing. And so what we've done is split this class. And what you'll see is in the class precedence list that those two have stayed together in the class precedence list. And spice used to be here, and now it's spice prime and flavoring. That is, we've split and taken those things which were just spicy and put them down here, and those things which are generic to flavoring, we've put them up here. And again, you see that those two have stayed together. And in the Common Lisp Object Standard, we've defined a topological sorting algorithm, which is fairly complex. But the most important thing about that algorithm is it maintains these constraints so that you get a very natural kind of inheritance from the class precedence list. Now, using that class precedence list, we can decide which method we want to use in any particular case. We want to use the most specific method which is defined. So if we have a method for colored square for moving, we will use that instead of the method for square. And this talks about combining applicable methods. I'll come back to that because there's a part of object-oriented programming which allows you to define pieces of methods and have those to be used together. Now, the first thing I want to do is talk about classical methods. It's classical because it's using the class of its first argument, and it's only the first argument that is going to be used. And it's also classical because it's been used for a long time in computer science, several years. So the way classical methods work is they search the class precedence list, and they find the first class that has a specified method. When we have multi-methods, what we want to do is look for the first difference in the specification of the method, the first argument that is different in terms of specification. And we use the left-to-right order to sort of search that argument order. But otherwise, it's just like the classical methods. And when we have individuals, the only thing that's different about individuals are more specific than any class. Now, it's this point I want to give you a brief look at how we can implement this sort of thing. Remember what I said was that the generic function itself implements this selection procedure. So there's four kinds of cases, and I'm going to go through each of the four in turn. For classical methods, how does this work? Well, a very simple way, as we said, is you go up the class precedence list. And here you have a tree, and it says a hypermeta complex number and a hypercomplex number and a complex number. If you have an instance of a hypermeta complex number, the first place where there's a print procedure is up here at complex number, and that's where you would find the method to actually do what you wanted to do. Now, if you had to search up that tree every time, that could be very slow. So what we have done is adopt something that was done in Smalltalk some time ago and make a special cache, a way of looking things up quickly, which doesn't always have the right answer, but when it does, it's very fast. So this cache has a class and a function as its keys, and with 1,000 entries, you get 98% hit rate, which is very good since you can afford to be 10 times as slow for the slow case and still only slow down this entire method thing by no more than a factor of 1.5 or 2. Now, the way it works very simply is you just simply use the address, the internal address of the class, and of the generic function as keys, and you do something like the logical exclusive OR, and you can find a position in this table. And if you use these two, and if it's here, then this is the code to use. So it's a very simple lookup table. Another way of doing it is instead of having a global cache, is to have a local cache, one for each generic function. And this is even faster to do the lookup because there's only one key, because the generic function is implicit because it's local to that generic function. So you only have to look up the class to find the function. And that's very fast as well. Now, a very important thing that we found out when we looked at object-oriented programming systems, Smalltalk, loops, flavors, every one we could get our hands on, is that most of the methods in the system are only defined once. That is, there's only one method for doing fratsets. Now, there may be a number of methods for doing move, but something between 50 and 75% of the methods have exactly one definition. And so for that case, the code is very, very simple. We could actually just go into the ordinary code. We don't have to do any lookup. Simply check whether the method is applicable or cause an error. So I've shown you here the code that is actually used. Sometimes you only have a default method. Here you don't even need to do your checking. This is a method which has no specializations. It doesn't say it's for any particular class. It's a method rather than a function because it's allowing users, later people, to specialize and add methods. And in this case, you don't even have to have any checking code. So it's no different than an ordinary function call. And it turns out to be a fair number of these as well. So what we've done in having an object-oriented programming system is provided a mechanism for organizing our code in ways that allow later specialization. But we don't always take advantage of it, and we see that that is something we can take advantage of when doing the implementation. Multi-methods. Multi-methods use a very similar technique, namely the slow lookup finds the most specific method. The caching, again, makes use of either a static sort of the methods. It knows which one it can use on any time, or it can use a general cache. And here's a picture of the cache. It's very similar to the one. You'll notice it has several different classes which it uses as keys, and then it just looks things up in that way. We haven't had a lot of experience with multi-methods, so we don't know how much that will slow things down, but it looks like it's not very much from what we can see of the implementation so far. Now, what I want to talk about now is a notion of method combination. One of the things we've said is that classes can specialize other classes. That is, you can write a method which uses what used to be there and then add something. And what happens is there's a procedural mechanism for doing that, whereas if you have a bordered window, special thing for moving, that is, move the border, please, you'd like to be able to say, and now, window, you do your stuff. And so there is a thing called call next method, which can be called inside of the move, which lets you say, oh, do whatever was here, and then come back to me. So it says, call the next method, move the window, and then redraw the border. So that's a procedural mechanism for combining methods. Another mechanism that people have used for combining methods is to be able to define pieces of methods and have those methods, those pieces combined at compile time. And here there is again, a little tree. And here there's a method called main. And here there's some before and there's some after methods. And the way in which a method for this 2D line would work is it would actually do the before method, and then this main method, and then that after method. And it wouldn't do that by searching, but it would have done it by combining all those things at compile time or at a method combination time. What I want to do now is to talk about the meta-objects which implement the system. The meta-objects provide an abstract interface to the implementation. And what they also do is, because they are actually causally connected to the implementation itself, that is, they are a reflection of what is actually going on, they allow the implementation to be extended in a portable way. For those of you who know Scheme, you know that they talk about the meta-circular interpreter. And what the meta-objects do is provide a distributed version of this kind of meta-circular interpreter, one that is based on the methods for the kinds of objects that are there. And finally, what it does is, because these objects are manipulable with generic functions of their own, this provides an interface for program development tools. So, for example, if we define the method draw on spline and window, we see that two different kinds of objects are created by virtue of the definition of this method. Namely, there's a generic function object which gathers all of the methods that are defined on draw. And there is a method object which has the special code that's good for spline and window. And what the generic function object does is it combines the information that's in all of these method objects. And it's the object that has as its job it has to build the discriminating code which will actually be run to choose the appropriate method code. Having the objects there allows the programmer to build special ways of interfacing with the object system so that, for example, a user interface could be used to develop certain methods for drawing which are based on, for example, direct manipulation of the interface. And the underlying programming system can add them in simply by doing this kind of add method that I illustrate here. So we add a couple of methods for draw. For example, the special one for my sketch, which says, this is an important one, make sure you blink. That may all be programmed by manipulation of the user interface rather than by actually writing this code. And the system itself can add this code. Now, in addition to this kind of programmatic manipulation, the generic functions and methods provide flexibility in other ways. For example, we could write special kinds of generic functions which could select its methods in very different ways. It could look at unification with logical unification. It could have new ways of combining methods. It could use constraints on the pieces of methods to decide what order they're supposed to go in. And they can also support certain kinds of optimizations. Another set of meta-objects are those that are the classes and that define the classes. We see here that a 2D point is an instance of the class 2D point. That class itself is an instance of a class, standard class. And standard class is what is built into the system to allow the appropriate kinds of support for our user base. It also allows the flexibility to be able to change the instance structure, get special kinds of slot access, to change the inheritance. We talked about the class precedence list. You may want to change how that thing is ordered. The classes can do that. And there's special ways of changing the class behavior because those are their objects themselves. The standard class supports special features which have been found valuable in object-oriented systems. For example, you can change the class of an object. Suppose you have a point which is represented by x and y coordinates. You can change the class of that to one that has the point represented by rho theta coordinates. Another kind of feature that's very important in a program development environment is that when a class is redefined, what you'd like to do is have the obsolete instances be able to be updated to the new class structure. And the standard class provides that kind of facility. So what I've done is give you a very brief overview of these meta-objects, which are a very important part of how the system is done. But the details will have to be left for another lecture. What I want to do is give you a very quick tour of how the process has gone on to develop a standard, because this is a very important part of computer science, is that we do a whole series of explorations, and then what happens is we standardize on some things. So what happened was there was a number of possible bases for the standards: common loops, common object, object Lisp, and new flavors. And there were presentations made to the special interest groups to have them evaluate this on the basis of the technical features that each of these supported. And after that time, there was a standards committee that was formed for the entire Common Lisp effort. That's called X3J13. It's a U.S. standards group. And there's a subcommittee, the Object Standards Subcommittee, which is made up of members from a number of different organizations, and with commentary that comes from all over. That is, we had a small number of group meetings, but we had a large number of messages over the various networks that connect the computer systems around the country. And this is a very important thing, that the way standards operations go now is that we can get immediate feedback using the network. And what we do is then incorporate those commentaries in a publicly visible and publicly editable document. Now, in addition to just having a specification, one of the things that's happened to make this standard spread fairly rapidly is there's been a portable implementation. It was originally a portable implementation of common loops, and now it's a portable implementation of CLOS as a publicly available implementation that can be obtained from Xerox. And that has been used by many organizations to experiment, to extend it, to test out the ideas that the meta-circular meta-object implementation really can provide the extensions that we want. And X3 has endorsed, the X3J13 committee has endorsed where we've gotten to. So now I want to give a summary of what's happened and where we are with respect to CLOS. What I talked about is a layered approach to building a standard. Namely, there's some basic programmer interface macros. These are things that make a language that's easier for programmers to use, like the def class and the def method and def generic. I've said something about the generic functions underlying the macros, and I've more importantly said that underneath all that there is a set of meta objects which have methods which underlie those functions. And there's more than one way to do a given operation, but each level would be used by a different user. So what we've seen is that all Lisp objects have class. Most Lisp systems before this simply added on objects. What we've done is incorporated. And the Common Lisp object system extends the Lisp type system. Every class is a type specifier. And methods can be applied to built-in objects like integers and consts. So what we've seen is an integration of procedure and object-oriented programming. This was the aim of the Common Lisp object system, is to make a very tight integration of these two styles of programming. What we've done is we've taken and merged the notion of types and the notion of classes, which were separate in most versions of object-oriented programming in Lisp, and made these two things, which seem very close, be the same thing. Secondly, what we've done is we've merged the notions of message sending and procedure calling so that there's only one way of invoking a behavior, and that is calling a procedure. This means that a user does not have to know how things are implemented. And by having those two, what we've seen is that we can go incrementally from a program which is implemented in a procedure-oriented style to one that is implemented in an object-oriented style. And finally, what we've seen is that by using this object-oriented programming style for the implementation, we can build this meta-object layer which provides not only for a hook into the implementation, but provides for future extensions. And so it's a new way of having a standard. It's a standard which provides both what's commonly used now in a useful way and provides for extensions and a path for the future. Thank you very much.
I'm Judith Lemon from University Video Communications, and our first question is from Purdue University. How could you combine this with strongly typed languages?
Well, strongly typed languages provide two different ideas. One of them is a notion of checking programs before they're run. And for that, we can imagine declarations that an environment for the Common Lisp object system could provide. And the other is mechanisms for making things more efficient, kind of optimizations that can come by having more knowledge. And we can combine that by saying that we're freezing a system at a certain point, and then the system can do certain optimizations. But we want to have it so that it can be, these optimizations can be released so that you can continue to get appropriate extensions to the programs that you've written.
The next question for you, Dan. What is the relationship between object-oriented and logic-based programming?
Well, these two seem very different on the surface, but one of the things that that has been come up recently is that the concurrent logic languages seem to have a very natural way of incorporating object-oriented programming in them. And some other work that's going on at Xerox and at Weizmann Institute and over in Great Britain and in Japan is the incorporation of an object-based paradigm within the concurrent logic languages. And it looks like by adding certain kinds of unification in the procedure call and by reifying, making real the communication channel between objects using the logic variables, you can get a very good combination which combines all of these paradigms in one integrated environment.
And for our final, less technical question, can you comment on the role of collaboration in your research?
Well, I've always found that the most productive way to work is to find other people who have lots of energy and to take ideas which are in their nascent stage and work with them to develop these ideas. As you saw, that there was a committee that was been developing the standard. The work that was done before that was done by a group of us at Xerox. And in every case, I have found that by working with a group of people, working with other people, the ideas grow big enough to provide more than enough credit for everybody and are always much better than any one of those individuals would have done by themselves. So I can't encourage students enough to really work collaboratively with people. But we have to learn in computer science to stand on the shoulders of our predecessors, not their toes.
Thank you very much. Excellent sentiment. And thank you for joining us today. We invite your comments and questions on this presentation, and we hope that you will also make nominations for future speakers and topics. If you're viewing this lecture on tape, there are postcards for this purpose tucked under the label of your video cassette. Otherwise, our address is at the end of the tape. Thank you again.